Hello everyone, welcome back to another lecture of COP-3402. Today we're going to be starting the second half of the course looking at compiler technology. So compilers are the tools which translate the C code you write to the machine code, the binary code that can be executed on your processor. Up till now, the way you've probably seen this working here is by using GCC just by itself. So let me show you an example. I have a file here called hello.c. All we do is include std.io and then use puts to print the string hello world to the console. Up till now, what you've done is just pass C files directly to GCC and specify your output files like so, and we can run this and actually execute hello world and it prints to the console like expected. Now, you might think that's all there is to compilation, but in reality, compilation takes place over multiple steps, each of which are shown here. Now, I'm going to go through these steps one by one with examples to show how they work. So the first step is to take the C source code that we actually write as developers and pre-process it, or expand the preprocessor directives in it. And we use a tool called the C preprocessor to do this. Now what this does is several things, but the thing that you're probably most familiar with is hashtag include statements, expanding those. So let's take a look at this. I'm going to use tmux here to split my screen in two. I'm going to open the hello.c file on the left here, and I'm going to run gcc with the -e flag. You do not need to remember this flag. I'm just showing you how the stages of compilation work. You do not need to remember this flag. GCC with the -e flag to expand the preprocessor directives on the left-hand side here. And I'm going to pass in this hello.c file as input and specify hello.i as the output. Now the conventional file name extension for preprocessed C source code files is .i. Now if I run this code and then look at hello.i, you can see we have many more lines of code in this file than we had in our original C source code file. So the reason for this is because the preprocessor actually expanded this include statement to expand to the contents of that file, std.io.h. So all the code you see here is code that is defined in std.io.h. There are some of these hashtag lines here, lines that start with the hashtag. These are like preprocessor, I don't know what you call them, comments or markers. They're not relevant for how our code actually runs. So you can see at the bottom of this file, though, we actually have the main function that we actually defined ourselves. Again, what we've done by running the C preprocessor on this file is expand standard.io.h to its contents. This includes declarations. The reason you'd want to do this is to obtain declarations of functions you have not defined yourself. So for instance, puts here, we have not defined puts in this C source code file, not ourselves, or declared it. But this header, std.io.h, contains the declaration of this function for us. So that's the main reason you want to use includes, to provide C source code with the declarations of functions that they have not defined themselves. All right, so that's preprocessing. Let's look at the next stage of compilation. And by the way, the preprocessor can do more than preprocess and expand include statements, but we won't go into that here. So now that we have our preprocessed C source code that ends in .i, we're going to pass it to the C compiler, GCC, to compile it to assembly code. So assembly code, you've probably seen before in your organization class, computer organization. You've probably seen MIPS assembly. We're going to be using a different flavor of assembly for this course, but you should be familiar enough with assembly to be able to understand it. And what we're going to do, what assembly is basically the highest level, low-level code you could write, or maybe the lowest level, high-level code you could write. Maybe that's a better way to say it. You can actually write assembly by hand because it is English for the most part, after all, English and numbers, but you probably wouldn't want to. But because it's still English, it's still ASCII text, you can't run it on your processor yet. So anyway, maybe I should just show this so you can see what I mean. Let's run the compiler here, GCC with the -s flag, to translate our preprocessed C source code file here, hello.i, to assembly code. Hello.s. Now, the conventional file name extension for assembly code is .s, so that's why we're specifying .s here. Now if I open this file up, you can see we have assembly code. You can see that our main function is actually defined right here. You can actually see the call to our puts function here as well. Now, what I was trying to say earlier, or show earlier, is that if I were to translate this or look at this code's hexadecimal contents using hexdump, so hd hello.s, you can see that we actually can view its contents using hexdump, and that call to call, which we saw earlier, let me actually delete this, find that, there we go, has some hexadecimal representation here, but the hexadecimal representation of call, the ASCII text call, is not the same as the byte code for the instruction for the call opcode, the bytes for the call opcode on your processor. That's what I'm trying to say. So we cannot run this assembly code directly on our processor. Instead, what we need to do is compile this assembly code to object file code, which is machine code that cannot be run by itself. So let's use a tool called the assembler to do this. So we're going to say as hello.i or .s, specifying hello.o as the output. The conventional file name extension for object files is .o. And now if we open hello.o, you can see we actually can't understand it at all. It's mostly incomprehensible. There's a few strings in here like hello.c that are embedded into this binary, but for the most part we can't understand it. And this is because this is binary code. This is not code that you're supposed to read or write yourself. So how can we actually view the contents of this object code? Well, we can use a tool called object dump to do this. So if I say object dump -d, we can disassemble the contents of this file. So -d hello.o, and we can actually see the disassembled contents of this object file. There's that call instruction again. Now we have the actual correct bytes for the call opcode here. And here is, let me see something else here important. Oh, right here. The target architecture of this object code, of this binary. So when I run a compiler, and this is something you may not be aware of, but when you compile your code to machine code, it has to be compiled for machine code that is capable of running on your specific processor, for your specific architecture. So here we have an x86-64 architecture, is what this object file has been compiled to run on. And the reason for this is because if you run lscpu here to show you my CPUs on my machine, I'm actually on an x86-64 architecture. And I have Intel CPUs. So if I wanted to run this code on ARM, it just wouldn't work. I would need to recompile it using a compiler for compiling C code to ARM. And back in the old days, this was the case. For every combination of front-end language and architecture there was, you had to write a separate compiler to handle it. Nowadays, we have ways to sort of mitigate this issue. I won't go into them in this course, but just keep in mind that originally, for each programming language that you wanted to compile to machine code, you had to write a separate compiler for each language and target architecture. Okay, so that's the disassembled output. Another thing we can look at with object dump is the symbol table with the -t flag. So hello.o. And now we can see the symbol table, also called a linker table. This contains all the symbols in this file. These are, now you can just think of these as like function names. There's more than that, but for now just focus on the function names. We can see that the main function is defined in the .text section of our assembly code. And the putS function, I'll show this up here again in the C file, hello.c. This putS function is actually undefined. UND stands for undefined. It's undefined in our C code, and that makes sense because we have not defined it in our C code. So if I were to try and run this, change mode u plus x on hello.o so I can actually try and run this binary, you'll see it actually doesn't work. And there's a few reasons for this. One of them is because this putS function is undefined. So how can we actually fix this definition? Because we were trying to access it by using this include here, but as we saw in the preprocessed source code, we only got the declaration of putS. We did not get the definition. Where can we get the definition of this function from? Well, that's where the last tool in this compilation tool chain here comes into play, the linker. So the linker, what it will do is resolve references to symbols that are undefined in a program that might be defined elsewhere. So this is actually more complex to run, so I'm just going to actually copy and paste this code here so I can run it. And what this will do is link our hello.o file against a bunch of object files in our implementation of the C standard library. And this will provide the definition of putS so that when we actually try and run our hello binary, it will work. Now there's an important distinction here. What we just used was something called dynamic linking. You can see that with this dynamic linker flag. That means that at runtime, the loader, which is the last step here, which is probably initiated by exec, some call to exec, the loader will actually resolve the names of symbols that are undefined when the program is loaded. So let me show you this. If I open main.c here again, oops, sorry, wrong file, hello.c. At a runtime, the linker is actually resolving and getting the definition of putS using these object files that we have linked this file against. And the way the linker knows where to look for these files, it varies. You can specify where to look for these files in argument variables. You can also embed that information directly in the program binary itself. But the big idea is we're not actually inserting the definition of putS in our hello.o file. So if I were to actually look here and show you with object dump -t hello.o, putS is still, or I'm sorry, not hello.o, hello. You can see that putS is still undefined. It's not defined in our C source code file, but it is defined in glibc. And so at load time, because we dynamically link this file, the definition will be resolved and our code will be able to execute. Okay, so another thing I want to point out here, let me look at the disassembly output of this hello.o file. Sorry, so hello.o is very small, you can see that, but if I look at the actual hello file now, there's a lot more content here. And this is because through linking, we actually add more code that enables our program to run. And this also is some code that enables the whole dynamic linking process to even work at load time. You can see here, like this actually shows us where to find the putS definition. So one more thing I want to point out about compilation to machine code here is that for our code to actually run, what the operating system expects to see in the binary file is not main. So we have main down here. This is the main function that we defined in our C source code. But in reality, in compiled object files, machine code files, there is this function called _start that wraps around main. You can see that here. It performs all these setup steps and then finally calls main on this line right here. So in our object files, or executable files, I should say, _start is really what gets run first. It gets run first. It's a wrapper function that sets up all the register values and whatnot for running main. Okay, so that was the whole process of compilation essentially for dynamic linking. So I want to go over another variant here, which is called static linking. So I'm going to run. I'm going to look at some code here that I have. Not intro.sh, static.sh, static linking.sh. I'm just going to copy this line here. You can see it's a lot longer than the last linker command that I ran. One thing I want to point out is that the linker program is unfortunately named LD. This makes you think it's the loader, but it's not. It's the linker. The loader is different. So I'm running a linker here with this -static flag to specify that I want to statically link these object files against my own hello.o object file. And the way this works, static linking, is a little bit different. So now if I run object dump -t on hello, you can see in the statically linked file, if I can search for this here, see if I can find this. Yeah, right here. PutS is defined in many places, actually, or in several places. Right here, actually. Here we go. PutS. It is actually defined in our C source code now. So static linking actually embeds the definitions of all symbols in the final binary. So definitions don't have to be resolved at runtime. And there's reasons why you might want to pick static linking over dynamic linking. They consume different resources essentially. With static linking, because you're copying the definitions of all used symbols into the final binary, the compiled binary is going to be much larger than if you dynamically linked it. If you dynamically link the binary, then you're not duplicating code, your binary is just resolving at runtime, at load time I should say, the names of symbols that it actually has that it needs in order to run. It's just looking at a pre-existing definition somewhere else in your machine. So you're saving some space, but the one of the costs there is that because you're dynamically looking for these definitions at load time, programs start a little bit slower and can sometimes execute a little bit slower. But overall, you save a lot more memory space by using dynamic linking. Okay, so let me look at the disassembled output here as well. If I look at the disassembled output for the statically linked file, you can see the disassembled output has much more content in it than the dynamically linked binary. And again, this is because we're copying the definitions of all the functions that we are going to be using, and all the symbols we're accessing directly into our final binary here. So that's dynamic versus static linking for the whole compilation pipeline here. Now let's take a look at a concept known as separate compilation. So you've probably seen this before, or used it before and didn't realize you were using this. Let's take a look at two files that I prepared here. I actually split my screen like this, so I'll split it like this and then do a horizontal split. So we'll say at the top I have this file f.c. All this does is return x times 2. It's a function f that just returns x times 2. And then in main.c, I have a function, I'm going to delete this declaration here, called main.c, or a file main.c. I have this function g, which is just returning f of 2. So this should just be 4, because 2 times 2 is 4. And in main, we're just printing what f returns. So if I were to run this with GCC, gcc-o main f.c hello.c or main.c, and then run main, and you'll see we get this implicit declaration of f warning, but it will actually still work, and I'm going to explain what that warning means in a second, but this will actually still work. We get 4 as expected. And now let's take a look at the actual phases of compilation for these two files separately. So GCC is compiling them both and linking them together for us, but really what's going on, again, is going to be every phase of this compilation pipeline is going to run for each of these files. So to execute these in turn, gcc-e, actually I have some code here I can just copy and paste. I'm going to compile both of these to assembly. And we get this warning again about an undeclared implicit declaration of f. And the reason for this is because if I look in the object dump output for this, or actually if I look in the assembly output, so main.s here, for this main file here in the bottom left corner, you can see that main is defined here, but the function f is just never defined anywhere. We don't have the definition of the function f anywhere in this file. G is here, but f is not here. And that's why we're getting that implicit declaration. Well, one reason why we're getting the implicit declaration warning is because our C source code is trying to call this function f, but nowhere in the C source code has it ever been declared. So we can silence this warning by just adding a declaration of f here. We don't need to define it, we just have to declare it. But for now I'm going to leave this commented out still, because the warning doesn't actually matter so long as we can still link the compile code, the object code for f, with the object code for main to resolve the definitions. The definitions are what's really important, because the assembly output still calls f. We can see that, well, it would still call f. Let me go back to the separate compilation sh file I had here. I'm going to compile these assembly files to object files now. So let's do that here. And now we have the compiled object code here. So let's take a look at this. So object dump -t f.o. You can see that we just have the definition for f. And for main.o, we can see that in the symbol table, printf is undefined because we're dynamically linking this against the standard library to get this definition. And we're also seeing that f is undefined because we are dynamically going to be linking, or actually, yeah, dynamically linking the definition of f here against the definition, or against the object file of for main. So let me go back to the source code here just to see the example. I can now just run GCC, passing these two object files here to compile this to a final main binary, and now if I run this, it actually works, because we'll be able to link these two definitions together. And the way to visualize this is to look at this chart here. We're essentially going from f.c and main.c to their corresponding object files and then linking them together to form a final binary. So even though main.c references f without actually having the definition of f anywhere inside of it, because we link them together to form main, the main function and g get access to the definition of f that way. And if we wanted to silence that error we saw earlier, so I'll show this again. If I ran gcc dash s f or main.c dash o main.s, we would get this implicit declaration of f warning. I can silence that by just actually adding a declaration of f in our C code. So that's why we need declarations, to silence these sorts of warnings for the front end of the compiler, the part that's actually reading the C code, to see that nothing is wrong with the way we're calling these functions. So speaking of function calls, that brings me to the next topic here. We've already saw main versus start. This is application binary interface. This is the next topic I want to talk about. So the C functions that we see here, like f, g, main, when we call a function, for instance, f of 2 here, the way we call this function in our C code is to pass arguments directly to it. But in assembly code, I can just look at some assembly code here as an example. So I can say vim, I don't know, hello.s. You can see in our call to call here, we're not passing arguments in the same way as we are in our C code. So if I go back to the hello.s file here, or .c file here, you can see it. We're calling put_s and passing the argument hello world here as a string, but in this call instruction here, we're not passing hello world directly into this function call. So how do function calls actually work in assembly? Well, the way they work is specified by an application's binary interface, by an application binary interface. This specifies things like how to pass parameters, how to pass return values, how the caller and callee should be responsible for setting up the stack frame of the call. And to give you a nice diagram to show all this will be the last thing we talk about in this lecture, I recommend checking out this webpage by Eli Bendersky, I'm not sure how to pronounce his last name. He works at Google. He's a really great engineer who has a blog all about programming language concepts and compiler tools. And he talks here in this blog post with this nice diagram about how application binary interface, ABI, actually works. And you can see here in this example, we have this function myfunc, which returns a long, and it expects 8 arguments that are all longs. And it also has 3 local variables, which are also longs. And what we can see is that the way the ABI specifies that this function call should work in assembly is that, we're not going to see the assembly code, but this is what the assembly code must do. We pass the first 6 arguments via registers. The remaining 2 arguments get passed onto the stack here, stack frame, at positive offsets from the RBP register value. So what this whole block here on the left represents is a stack frame, and what a stack frame allows us to do is basically do things like recursion. So we basically save the state of each function call in a stack frame, and with stack frames you can actually implement recursive functions, because every time you make a new call to a function, you just make a new stack frame and then save variables at different offsets from that RBP value for the frame. And you can see that local variables are stored here as well. We have x, y, y, and z are stored here. These are our local variables. Parameters are stored here. The return address is stored here. The stack frame contains all this information. And every time we make a new call to a function, we create a new stack frame for it. Now, this is important because if we didn't have stack frames and all we did was just use a jump instruction to go to the place in memory where each function was defined whenever we wanted to run a new function, then recursion wouldn't work, and other function calls wouldn't just work correctly, because we would be overriding the values of variables and local arguments and parameters each time we made a new function call. So that wraps it up for this lecture. We're going to be going over all these concepts in more detail in a later lecture, but I hope this was sort of a broad introduction to compilation. Your next project is going to be literally, I'll open it up here, this into post project. It's not published yet, but when you check it out, you're literally just going to be copy and pasting text in an image file, just writing it by hand. It's an exercise, not a project, so it's due sooner than it normally would be, so 1 week. But it shouldn't be very difficult. You're just copy and pasting code from an image file into a text file, basically. So yeah, this is to give you a gentle introduction to, again, compilation tools. Okay, so if you have questions, come see me during office hours, and goodbye.